Good evening, all who is present here. It's my privilege to extend a warm welcome to Mrs. Indumati, an exceptional individual whose journey of academic and professional excellence serves as an inspiration to all of us. Mrs. Indumati's academic path began at Dhanavishmi College of Engineering and followed by her Masters at Residential College,
Yeah, good evening. Am I audible?
Yes,
Thank
ma'am.
you. Good evening, everyone present here. First of all, I want to thank my supervisor, Dr. Ghulam Nabi Al Sad sir, for giving me this opportunity. So, as a budding engineer, a budding engineer, I feel grateful for this opportunity. Let me share the screen now.
Yes, ma'am.
Is my screen visible?
Oh, yes, ma'am.
Okay, thank you. Okay. So today's topic is microstrip patch antenna design and evaluation. So today it's going to be an hands-on session. I hope everyone have installed CST Micro Studio in your PC. Okay, let me move on to the session. So today we are going to discuss the introduction to microstrip patch antenna and what are all the different shapes of microstrip patch antenna and what are all the different feeding techniques we can use to design a microstrip patch antenna. And then we are going to take a problem and we are going to solve a problem. And then using CST Microwave Studio, we are going to design a microstrip patch antenna and then we are going to analyze the parameters of it. So, introduction to microstrip patch antenna. It is also called as a planar antenna and printed antenna, or it is simply called as a patch antenna. So, this microstrip patch antenna is of resonant type. So, it is a narrowband antenna. So, it is very simple to design. Yes.
Ma'am, are you presenting any PPT or presentation?
Yes. Yes.
The PPT is not visible, ma'am. We can only see your Gmeet page.
It's Let me share it again.
Okay, ma'am.
Now is it visible?
Yes, ma'am. It is visible now.
Thank you.
Thank you, ma'am.
Okay. Okay, let me start from the beginning. Okay, so microstrip patch antenna, it is also called as a planar antenna or printed antenna, or simply we can call it as a patch antenna. So this microstrip patch antenna is by default it is of resonant type. It is of narrowband antenna. It is very simple to design. So it is very
Excuse me,
inexpensive.
ma'am. Ma'am,
Yes, yes,
could
yes,
you show it in a full screen, ma'am?
yes.
Could you show it in a full screen, ma'am?
No, I have used a slideshow.
Ah,
It's not showing full screen. Now is it fine?
no, it is not changing, ma'am.
Now is it visible?
Visible, your PPT slides are visible, ma'am, but not in full screen mode. Maybe it's not changing.
Okay.
It's okay, ma'am. You can continue, ma'am.
I'll share it again. I couldn't able to share. I don't know why. Yeah, it's enabling now. Now is it visible?
Visible, ma'am, but same as before. It's okay, ma'am. We can continue.
But I have.
Maybe some network issues.
Is it any from my side? I think.
You can continue. We can continue, ma'am.
Okay.
Just okay, okay.
Thank you. Thank you. Okay, so it is inexpensive because we are using a PCB technology, printed circuit technology, and application of this microstrip patch antenna we are using in mobile phones. In our mobile phones, we are using MIMO technology, that is multiple input, multiple output technology, and then in Wi-Fi we are using microstrip patch antenna, GPS, Bluetooth, satellites, missile applications, aircraft, spacecraft, and also vehicle to vehicle communication. For example. In order to avoid the collision between two uh, vehicle, we can use a microstrip patch antenna to detect the distance between two vehicle, and we can avoid the collision between these two vehicle. So, can you see this image? Microstrip patch antenna. So you know how it is constructed, right? We have a ground plane and we have a substrate, and the radiating element is a patch. It's a simple rectangular patch antenna. So once you applied a feed to this microstrip patch antenna, so this is your feed line. So we have to apply a feed to this microstrip patch antenna. Once you have applied a feed to this microstrip patch antenna, so it radiates electromagnetic waves into free space. So can you see the
Excuse me,
feed?
ma'am. Sorry
Yes.
to interrupt you again. The page is still in the first page, ma'am. We are not able to
Yes.
see the image.
Yes, still. Uh, yes, I'm still in the first page.
Okay, okay,
You
okay,
can't
ma'am.
see the. You
Now it
can't
is
see
fine, ma'am.
this microstrip content.
Now it
Now
is
is it
visible, ma'am.
visible?
Yes, ma'am.
Okay. Okay, I'll continue like this. Okay.
Yes, ma'am. Yes, ma'am.
Yes, thank you. So can you see the field lines from ground to patch and patch to ground? So you have a conductor as your ground plane, and you have a patch that is also a conducting material, and in between you have a dielectric medium or a dielectric material. So if two conductors separated by a small distance, it can act as a capacitor, right? So once you apply a feed to a microstrip line, so once the impedance gets matched, so it causes a fringing effect. Okay, so this, can you see the feed lines from ground to patch and patch to ground? So this radiates an electromagnetic wave. This is the main reason to for microstrip patch antenna to radiate in electromagnetic waves. Okay, so let me show you a fabricated rectangular microstrip patch antenna. The first image is just a front view of the microstrip patch antenna, and the second image is a back view. So here, can you see the connector here? It's called as an SMA connector. So through this, we'll be applying a feed to the microstrip patch antenna. Just an example how a fabricated microstrip patch antenna looks. Okay, and then different shapes of microstrip patch antennas. So we have square, rectangle, dipole, circular, elliptical, triangular, this sector, and then circular ring sector. So this shape, you have a liberty to design your own antenna. It need not be just a square or rectangle or dipole or circle. It can be of any shape, but it should have a proper physical interpretation. You can design your own antenna, but each shape and size of an antenna radiates at particular frequency. Okay, so these are all the basic structures of microstrip patch antennas. Can you see the full screen, or else just can you share the full screen now? Can you see the full screen? Can anyone acknowledge?
No, ma'am, we can't see the full screen.
Okay,
But it is
okay,
visible,
fine.
ma'am. You can continue.
Yes, fine, fine. Fine. So far we have seen the introduction to microstrip patch antenna and an example of a fabricated prototype here, and different shapes of microstrip patch antenna. Next, we are going to discuss about the different feeding techniques of microstrip patch antenna. So we have two types of feeding. One is contacting type, another one is non-contacting type. Contacting type. So in the last session, you have seen the microstrip line feed, right? It is one type of a contacting type. So microstrip line feed and coaxial probe feed is a type of a contacting one. And coming to the non-contacting type, we have proximity coupling feed as well as aperture coupling feed that we are going to discuss in detail. So in the first image, so in the last session, you have seen how to design a microstrip patch antenna, a simple rectangular microstrip patch antenna, and how to that means how to feed and how to design this. All these things you have seen in the last session. So today we are going to mainly focus on coaxial probe feed. So this microstrip line feed is a conducting strip. It's just a conducting strip. So the width of the microstrip line feed is comparatively small when compared to your patch width. Okay. So why we are going for this microstrip line feed is it is very easy to fabricate. Okay. When coming to the coaxial probe feed, so how your coaxial probe is constructed, you have an inner conductor as well as you have an outer conductor. So in between you have an insulator or a dielectric material, right? So this inner conductor we have to add, that means you have to attach this inner conductor to the patch as well as the outer conductor to the ground layer. Okay. So why we are going for this coaxial probe feed is we can apply the feed at anywhere in the antenna. That means whatever the position you want to give a feed, you can apply a feed. Based on your design, you can choose whether you want to give a microstrip line feed or whether you want to go for coaxial probe feed. And the third feeding technique is the aperture couple feed. So aperture, so can you see the image here, aperture couple feed? So in the top layer, you have one dielectric material. In the bottom layer, you have another dielectric material. In between these two dielectric material, you have a ground plane. We have used a microstrip line feed in between this, and we have made a slot in the ground plane. So this is a non-contacting feed type, okay, feed technique. So this field is coupled from the microstrip line feed to the radiating element, that is your patch, through a slot cut in the ground plane. So you have to make a slot in the ground plane. Can you see the slot here? So we have to make a slot in the ground plane. So this is, so why we are going for the aperture coupled feed is to enhance the bandwidth. So as I have mentioned in the introduction itself, it's of narrow band, right? So microstrip patch antenna is of narrow band. So if you want to go for broadband, you can go for aperture coupled feed. And the last method is, the last feeding technique is proximity coupling feed. So you can just see this image. Proximity coupling feed, we have used two dielectric material, epsilon R1 and epsilon R2. That is, you have two dielectric constant. And we have a patch as a radiating element. So your two dielectric material or two substrate is stacked here. Okay, so this technique is also used to enhance the bandwidth. So feed line is placed in between the patch and the ground plane separated by two dielectric medium. Okay, so if you want to go for bandwidth enhancement technique, you can go for this non-contacting type. Otherwise, based on your design, you can choose whether you want to go for the microstrip line feed or coaxial probe feed. Okay, any doubts so far? So now we are going to enter into the design of rectangular microstrip patch antenna. So I want you to note down this problem and you can solve later. So that you can have a track how to design a microstrip patch antenna and how to design it. Okay. So design a rectangular microstrip patch antenna using FR4 substrate. So here we are going to use a substrate as FR4. The dielectric constant of FR4 is 4.3 and the height of the substrate is 1.6 mm.
Ma'am, excuse me, ma'am.
Yes, yes.
Ma'am, could you please change the slide?
I've
Yes, ma'am.
changed it.
Yes, ma'am. Thank you.
Is it visible now?
Yes, ma'am.
Okay, fine. So can you note down this problem? So today it's going to be an hands-on session, so it will be interesting if you interact with me. So we are going to design a rectangular microstrip patch antenna. So the design consideration, first of all, whenever you want to design a microstrip patch antenna, you have to remember three things, three design consideration. One is your dielectric constant, another one is your resonant frequency, and then height of a substrate, okay, height of the substrate. So in this problem, they have given dielectric constant as 4.3 and the resonant frequency as 5.6 and the height of the substrate has 1.6 mm. So step one, you have to write the given data, and step two, you have to calculate the width of the patch. Okay, so the width of the patch is represented as W. W is equal to V naught is nothing but the free space velocity of light divided by 2 into the resonant frequency in the square root of 2 divided by the dielectric constant plus 1. Have you all note down this equation? Shall I move on to the next slide? So today you're going to design a rectangular microstrip patch antenna along with me. So you can discuss in the, thank you. You can discuss in the chat box also. Okay. Step 3, once you have calculated the width of the microstrip patch antenna, step 3, you have to calculate the effective dielectric constant. Okay. So the effective dielectric constant is given as epsilon r plus 1 divided by 2 plus epsilon r minus 1 divided by 2 into 1 plus 12 into h divided by w the whole power minus 1 by 2. So from step 2, we can calculate the width of the patch. So once you got the value of W, you can substitute in this equation. You can get the effective dielectric constant. Okay, just note down this equation. So the value of epsilon r is 4.3 and the height of the substrate is 1.6 mm. So directly you can substitute the value. You can find out the relative dielectric constant. Sorry, effective dielectric constant. Once you have calculated the effective dielectric constant, you have to calculate del L. Why we are calculating del L? Because of this fringing effect. Okay, so once you have applied a feed to this microstrip patch antenna, the actual length is not same actually. So due to this fringing effect, your length of the microstrip patch antenna varies. So we have to calculate the actual length of the microstrip patch antenna. For that, we have to calculate del L. So del L is equal to 0.412 into height of the substrate. So from step 3, you can calculate the effective dielectric constant. You can use here. So effective dielectric constant plus 0.3 into W is nothing but the width of the patch divided by the height of the substrate plus 0.264 divided by effective dielectric constant minus 0.258 into W by H plus 0.8. So from this step 4, you can calculate del L. Okay. Have you all note down the equations? So once you calculate the value of del L, then we have to calculate the effective length. So effective length is given as c. C is nothing but the velocity of light. So c divided by 2 into fc into square root of effective dielectric constant. So first you have to calculate the width of the patch. The second thing, you have to calculate the effective dielectric constant. Third thing, you have to calculate del L and then the effective length. Okay. Have you all note down all this equation? Shall I move on to the next slide?
Yes, mom.
Yes. Okay, thank you. So the step 6 is to calculate the actual length, okay, of the patch. So from the previous step, you can calculate the effective length of an patch. So L, the actual length is given by effective length minus 2 del L. So you can calculate the actual length of the patch using this equation. So from this, we can able to calculate the length of the patch, the width of the patch, and then, but we don't know what is the length of the ground plane as well as the substrate, right? So length and width. So theoretically, we can calculate the width of the ground plane as 6 into height of the substrate plus W. And your length of the ground plane as 6 into height plus length. But practically, we'll be considering it as the width of the ground plane as 2 into the width of the patch and the length of the ground plane as 2 into the length of the patch. Right? So I hope you have noted all this equation. Quickly, we'll move on to the design. So this is coaxial. Yesterday, like in the previous session, you have seen how to design a microstrip patch antenna using a feed line, like microstrip feed line. So this is the second feeding technique, that is your coaxial probe feed. So can you see the inner pin here? This is your inner conductor, and so you here you have a ground and then patch. So in between there should be a substrate, but to visible, in order to view the inner pin, they have just to hide the substrate. So the middle one is your inner conductor. Can you see the coaxial port? That is your outer conductor. Okay, so we are going to design this. And then in the last session, you have seen how to design a patch antenna, right? So if you know the length and width of an patch, you can design a rectangular patch antenna. So we'll start designing it. So if you have CST Microwave Studio, kindly you just start the design with me. So we have to go to new template, microwaves, an RF or optical, choose antennas, click next. We are going to design a patch antenna, so choose planar and then click next. So let it be in the time domain. So we are going to design a microstrip patch antenna. The resonant frequency is in gigahertz. Obviously the dimension will be in the millimeter. Give next. Now today we are going to design a patch antenna for 5 gigahertz. So I'll choose and select all this electric field, magnetic field, far field, power flow, and power loss. Okay,
Excuse me, ma'am.
click
Ma'am,
next.
ma'am, the
Yes,
CST screen is
yes,
not
dear.
visible. Can you share that screen, ma'am? This PPT screen is still visible to us.
Oh, I think I have to stop and I have
Ah,
to
yes, ma'am.
share.
Ah, please, ma'am.
Thank you. Thank you. Is it visible now?
Yes, ma'am.
Yes, ma'am.
Okay. Okay, let me start from the
Yes, ma'am,
beginning.
it's
Okay,
visible.
you have seen, right? Go to new template. Okay, just go to new template, choose microwaves, RF and optical, click antennas, give next. Okay, so now we are going to design a microstrip patch antenna. So choose planar, click next, then click next, next. So the resonant frequency is 5 gigahertz. So I'm choosing 4 to 6. And I'm selecting all this electric field, magnetic field, far field, power flow and power loss. So if you're not selecting this, even after designing an antenna, we can simulate there. But okay, just click next and then finish. Everyone completed the process? Can you see the reference plane?
Yes, ma'am.
Yes. Okay. Okay, so once you get the reference plane, now we'll start designing a microstrip patch antenna. Can you see my PPT? Is my PPT is visible?
Yes, ma'am.
Yes. Okay. So I have calculated and I have just given the values here. You just note down the values. For this particular value, let's design a microstrip patch antenna and then we'll use a coaxial probe feed. Okay. So the width of the ground plane here, it is 36.8 mm and the length of the ground plane is 27 mm. And the resonant frequency, we are going to design an antenna for 5 gigahertz. And width of the patch is 18.4 mm. Length of the patch is 13.5 mm. And the thickness of the conductor, that means the thickness of the ground plane and the thickness of the patch is same. Okay. By default, it is the readily available in the market is 0.035. So you can use 0.035 as your thickness of the patch as well as for the ground plane. Okay, and the thickness of the substrate is 1.6 mm. And now I'll be explaining about this, the radius of the inner conductor, how to calculate this. I'll explain once once I'm designing it, and the thickness of the outer conductor, all these things, feeding position, we'll discuss. Okay, so just note down the width of the ground plane, length of the ground plane, what is the resonant frequency, what is the width of the patch, what is the length of the patch, what is the thickness of a conductor, that means the thickness of the patch as well as the ground plane and thickness of the substrate. Fine, have you all note down these values? Done?
Yes, ma'am.
Yes, okay. Okay, let's start designing it. So here you can see the perspective, the front view, the back view. So whatever you feel comfortable, you can choose the front view or back view, whatever. I always feel comfortable using the front view. Okay. So first, let's start designing the patch antenna. So first, go to you have just given the value and you have seen how to design a microstrip patch antenna. Today, let's discuss how to give a parameter so that during the optimization process, it will be very easy for you. Okay. So I'm going to name the width. So as you see in this image, x-axis is nothing but your width, as well as the y-axis is nothing but the length of the microstrip patch antenna. So x-axis I'm going to give width. Okay, so since it's a ground plane, I'm going to name it as WG. Whatever name you want to give, you can give. So for better understanding, I have given WG. Okay, so WG by 2, and here WG by 2. The y-axis, it should be the length of the patch or the length of the ground plane. So it is minus HG divided by 2, and then plus LG divided by 2. Fine. So the reference plane, I just took it as 0. I'm going to construct a ground plane on the reference plane. So the thickness of the ground plane is 0.035 mm. So I'm going to give T as a thickness. Okay. Any doubt? Shweta, can you unmute, please? Sorry, can you mute? Oh, thank you. Fine. So T is the thickness of the ground plane. Okay. Now we have to choose a material. So you just click this. Choose load from material library. And then, as I have mentioned earlier, ground plane, it should be a conductor. You can choose aluminum or you can choose copper, or whatever the conductor you want, you can choose. I'm going to choose a copper. So choose copper annealed. Okay. Then give load. Fine. Have you all done up to this? I'll ask anyone to share the screen. So next step. Still not visible.
Ma'am, your screen is not visible, ma'am. Like the software is not visible to us.
Is it visible now?
No, ma'am. Oh, it's visible now, ma'am. Ma'am, you didn't unmute yourself, ma'am.
Sorry for the inconvenience. My laptop got hanged. I couldn't do anything for a while. I'll continue now. Okay, shall I continue?
Yes, ma'am. Yes, ma'am.
Okay, thank you. Now we are going to construct a ground plane. So just go to modeling, click brick, and then press escape. So I'm going to name this as ground plane. And then the width of the ground plane is minus WG by 2 and then WG by 2. Okay. And in y-axis, I'm going to define the length of the ground plane. It is minus LG by 2 and then plus LG by 2. Okay. And then I'm going to give, so this reference plane, I'm going to consider it as 0. So I'm going to add the thickness in the z direction. Okay, so I'm going to give the thickness of the ground plane as t, just t. Okay, so now I'm going to load the material. So just click this, give load from material library, and then choose copper. You can choose copper or aluminum. So now I'm going to choose copper, give load. Okay, once you have choose a material, you can preview it. It will ask the dimension of the width of the ground plane. Okay, so what is the dimension of the ground plane? It is 36.8 mm, right? So I'm going to give 36.8. And what is the length of the ground plane? Can anyone say what is the length of the ground plane? It is
27 millimeter.
27. Thank you. It is 27 millimeter. So the length of the ground plane is 27 millimeter. Give OK. And as I have mentioned earlier, the thickness of the ground plane as well as the thickness of the patch is 0.035 mm. So 0.035 is the thickness of the ground plane. Okay. So you can preview it. Give OK. Now we have constructed the ground plane. Okay. Can you view? Can you see this? Zoom it. Dimension. Now you have to construct the substrate. Okay, go to modeling, click brick, press escape. Now I'm going to name it as substrate. So the dimension of the substrate is same as the dimension of your ground plane. So let it be WG by 2 plus G by 2 minus LG by 2 and then plus LG by 2. Now I'm going to construct a substrate on top of the ground plane. So the Z min should be the thickness of the ground plane. Then the Z max should be the thickness of the ground plane plus the height of the substrate. Any doubt in this? Any doubt in this?
No, ma'am.
Fine. So now we have to choose a material. So in the problem we have seen the dielectric constant is 4.3. So we have to choose FR4. So choose lossy material. So can you see epsilon is equal to 4.3. So your dielectric constant is 4.3 for FR4 material. You can choose FR4 lossy, give load. You can preview and then it will ask, because still now we have not given the value for H. That is the height of the substrate. The height of the substrate is 1.6 mm. Okay, and then click OK. Now we have constructed the ground plane as well as the substrate. Right. Now we have to construct a patch. We have to design a patch. So the same procedure, go to modeling, click brick, and then press escape. I'm going to name it as patch. So what is the parameter I have given for the length and width of the patch? Just W and L. So the width is 18.4 mm and then the length of the patch is 13.5 mm. Okay. So the width is minus W by 2 to plus W by 2, and the length is minus L by 2 to plus L by 2. So you have to place a patch on top of the substrate. Okay. So from the reference plane, the thickness of the ground plane is T and the substrate thickness is H. So the Z-min is T plus H. Now we have to construct a patch on top of the substrate. So it should be T plus H plus again the thickness of the conductor T. Okay. So the radiating element is a conductor. So I'm going to choose a copper. So from the already we have load the material, so it will be available here. So you can directly choose a copper, give preview. So it will ask the dimension. So the dimension of the width of the patch is 18.4 mm. So just give 18.4. What is the length of the patch? 13 point. It is 13.5 mm. Right? Now we have constructed the patch. That's all about the construction. Now we are going to apply a feed. So for any doubt up to this, you can view the parameter here. So in 3D you can view the structure, and in schematic you can view the parameters and its corresponding values. So WG is 13.8 mm, LG is 27 mm. Directly, if you want to change the dimension of any parameter, you can directly give, you can change the dimension here, and the thickness, height, length of the patch and width of the patch you can view here. Right? Now we have to give the feed. Once you have designed, you have to give the feed. Okay. So how to give a menu, and then go to macros, calculate, and then calculate analytical impedance. Okay. So first, so this is your home PBS. Go to macros, click calculate analytical impedance. What is the dimension of the inner conductor, and what is the dimension of the outer conductor, and we have to match the impedance also, right? So the frequency what we are going to design is 5 gigahertz, right? So epsilon r, I'm going to choose 2.1 as my inner insulator. Okay, so just give calculate. You can see Z0 is equal to 28.68. Okay, we should get at least approximately equal to 50 ohm, because your input impedance should match with your load impedance, right? Your characteristics impedance should match with your load impedance. So here I'm going to change the dimension of the inner conductor as well as the outer conductor. So small d represents the dimension of the inner conductor and capital D represents the dimension of the outer conductor. Okay, so I'm going to increase the dimension of the outer conductor, give calculate. So you can observe your characteristics impedance got increases, right? So let me give 3, give calculate. I'm going to give 4. 4 point, I think it is 4.7. So it is, so the dimension of the inner conductor is 1.4 mm and the dimension of the outer conductor is 4.7 mm. The inner conductor and outer conductor. Please note down the dimension of the inner conductor and outer conductor. Right? Then just give exit. So to construct a coaxial probe feed, to apply a feed using a coaxial probe, first you have to cut the ground plane. So because here you can see they have cut the ground plane, and then we have to give an inner conductor, it should touch the patch. Okay, so I'm going to cut the ground plane. Just go to modeling, choose cylinder. Okay, choose cylinder, press escape. I'm going to name it as ground cut. Okay, the outer radius is nothing but d, right? So let it be d by 2 and inner radius is 0. I'm going to give the x center as xf and y center as yf. Fine. Now I'm going to cut only the ground plane. The thickness of the ground plane, it starts from 0 to d. Right? So if you want to cut a conductor, if you want to make a slot in the conductor, you can choose a material as vacuum or else PEC. Okay. So I'm going to choose vacuum. Give preview. What is the dimension of the outer conductor? It is 4.7 mm, right? Give OK. It is asking the X position as well as Y position. I'm going to give it as 3.5. We can also change the position of the feed. Okay. So it's just showing. Just click OK. Now you have to choose cutaway highlighted shape. Okay. Just click cutaway highlighted shape and then give OK. Okay. Now this particular portion for this 4.7 mm, I have cut the ground plane. Can you see? Any doubts so far? Shall I proceed? Are you all designing with me? Have you all done this? Ground cut?
Ma'am, could you repeat the cutting part along?
Yes, yes, sure. See, if you want to ignore this step, you can directly give Control Z. Okay, fine. You can give Control Z and we can start the process again. Just go to modeling, click cylinder, press escape. Okay, I'm going to name it as ground cut. Now the outer radius is what we have observed. What is the dimension we have observed? It is 4.7 mm, right? So directly we can give it as D divided by 2, and then inner radius is 0 because we are going to cut the entire dimension, and give x center as xf and y center as yf. I'm going to cut only the ground plane. So I'm going to start from the reference plane till the ground plane I'm going to cut. Okay, the thickness of the ground plane is T. Fine. So if you want to cut a copper or material, you can choose PEC or else vacuum. I'm going to choose vacuum and then I'm going to cut it. Okay, just give preview. So you can see where you have to cut. Already I have given the dimension for XF and YF. That's why it's default. It is showing. If you have not given the values, it will ask for the value. Right? Then give OK. After that, give cut away highlighted shape. So this particular shape got highlighted. We are going to cut this highlighted shape. Okay. Just click cut away highlighted shape. Click OK. Is it clear now?
Yes, ma'am.
Okay, thank you. Thank you so much. Now we are going to construct an inner conductor. Okay. So the same procedure, go to modeling, click cylinder, press escape. Fine. So this is your inner conductor. I'm going to name it as inner pin. Right. So the radius, let me take it as R1 or whatever the name you want to give as per your wish, you can give. So R1 divided by 2. Okay. And X and Y center is same, that is XF and YF. Kindly note down, you have to construct the inner conductor. It should touch the radiating element, that is your patch. Okay. Minus 3 into 1.6, that is I'm going to extend below the reference plane. Okay. And Z max, or else you can give your Z min is the thickness of the ground plane plus the height of the substrate plus the thickness of the patch. From then, you have to give minus 3 into the height of the substrate. This is why, because you are going to connect an SMA connector. So you have to, from the reference plane, you have to give minus 3 into the height of the substrate. Okay. Definitely it's a conductor, right? So we have to choose copper as a material. Just preview it. What is the dimension of the inner conductor? It is 1.4 mm, right? Give OK. So let me show you. Can you see the inner pin? Can you see the inner pin? It is touching the patch. Can you see? It is touching the patch. So this is our inner conductor. Can you view it? Have you all done? Shall I proceed? Okay. Okay, let's construct the outer conductor. Or else, okay, first let's construct the outer conductor. The same procedure, go to modeling, click cylinder, press escape. It's an outer conductor, right? or outer pin, just an outer pin. So the outer pin dimension is d by 2. Okay, and then d by 2 minus 0.1, because we are going to construct an insulator inside the inner conductor, in between the inner conductor and outer conductor. So I'm going to choose the thickness of the outer conductor as 0.1. Okay, so it starts from d by 2 till, that means the thickness is 0.1. And you can choose the same x center and y center as xf and yf. And
Hello, ma'am.
yes,
Sorry to
yes,
interrupt.
yes.
The capital D is radius only, ma'am. Why should we have to divide it by 2?
Actually, while you're designing length as well as the width of the patch, it's a reference plane, right?
Okay, ma'am.
So how you will construct, how you will design a patch? For example, if it is 10 mm, you will choose in the negative x-axis you will be choosing minus 5 mm. In the positive x-axis you will be choosing plus 5 mm.
Yes, ma'am.
Right? The similar way. Can you understand?
But as it is a rectangle, we have to symmetrically position it in the coordinate axis. We are dividing it by positive and
By 2.
negative.
Yes, yes,
Radius is
yes.
a measurement. Yes, ma'am.
Yes, that's fine. But here you can't give entirely 4 point, sorry, I think 4.7 mm, right?
Yes, ma'am.
It should divide, it should, we have to consider the half of the, that means that is the diameter. We have to consider the radius. What is the
Okay,
radius
ma'am.
of a circle? It should be the diameter by 2, right?
Yes, ma'am. Okay, ma'am. All right. Thank
That's
you.
fine. Did I close it? Okay, let me again construct it. I think an outer pin, right? It is d by 2. See, whatever the name, whatever the parameter you want, you can give. Okay. So I just mention it as diameter. So I just took it the reference as d. Actually, can you see it is of outer radius and inner radius? Okay, it's a radius. It's not actually the diameter. Fine. Okay. So it is d by 2 minus 0.1. Okay. So it is xf and the y center is yf. Okay, minus 3 into height. Okay, so here we are not going to give this outer conductor to the patch. We are going to add the ground plane as well as the outer conductor. Okay, so we don't want to give the thickness as 0 t2h t plus h plus t. Okay, let it be 0. So the outer conductor is also a copper. Okay, so you can preview it, then click OK. Can you see the outer conductor? So this is your inner conductor and we have constructed the outer conductor. Now we have to construct the insulator, okay, or the dielectric medium. The same procedure, click cylinder, press escape. Let it be any name. Let me choose, okay, insulator. Now, what is the outer radius? It is d by 2. See, at this point, it is d by 2. So I have choose the width as, the thickness as 0, that means d by 2 minus 0.1. So the outer radius should be d by 2 minus 0.1 till the inner conductor. Okay. So what is the parameter I have given for the inner conductor? I think it is R1, right? And then the x center is xf and y center is yf. and you can give the Z min as 3 into 1.6 or else H. Okay. Now you have to load the material. So when we determine the dimension of the inner conductor and outer conductor, we have given epsilon r as 2.1, right? So we have to choose a material of 2.1. So this PTFE has the epsilon r as 2.1. The dielectric constant of this material is 2.1. So I'm going to use this material. Okay. Give load. Preview it. So can you preview it? It is not just an R1, it is R1 by 2. It is radius. Okay. So for any doubt in constructing this coaxial probe, now I'm going to give a port, the feed, and we are going to analyze the result. So for any doubt, shall I proceed?
Yes, ma'am.
So this, any doubt so far? Oh, now can you hear me?
Yes, ma'am.
Oh, any doubt in this?
No, ma'am.
Okay, fine. Now let's simulate it. Go to setup solver. In the same simulation, go to setup solver, give apply, and then give start.
Indu ma'am, your screen is not visible, ma'am.
Is it visible now?
Your screen is visible.
Thank you.
Uh,
Did you saw how I've applied the waveguide port as well as how I started the simulation, or you want me to repeat this step again?
Ma'am, could you please repeat, ma'am?
Fine, fine. I'll stop this. Okay, fine. So once you have constructed the waveguide port, just go to simulation, click waveguide port. So the distance to the reference plane, it should be -3 into the height of the substrate. You can directly give this. Again, I'll delete the port and I'll give, okay. Fine. So we'll be choosing the inner conductor. As well as the outer conductor. Go to waveguide port. It's taking time. Right? Just give -3 into the height of the substrate. Give preview and then OK. Fine. So once you have constructed the port, just go to setup solver. It's in the simulation. Go to setup solver, give apply and then start. Have you all done this? Have you all done? Any doubts so far?
Excuse me, ma'am.
Yes, yes.
Ma'am,
Just
is
let
the
me know.
simulation process after constructing insulator, ma'am?
No, first you have to construct an inner conductor, then an outer conductor, then an insulator. After, oh, yes, I have missed a step here. As I have mentioned earlier, we have to add the ground plane as well as the outer conductor, right? We are not done it.
Yes, ma'am.
Yes. I'll again do it, okay? So here we have a ground plane and then we have the outer pin. You have to add this ground plane as well as the outer pin, okay? So you just choose the ground plane as well as the outer pin, that is your outer conductor. Go to Boolean, give add, okay? Then we have to add the inner pin as well as the patch. Okay, you can just choose the inner pin as well as the patch. Go to Boolean and then add. Okay, so now I have just what I have done is I just added this outer conductor as well as the ground plane and then the patch and the inner conductor. Fine. Now we have to apply the port. Faces. Just press yes. Select the inner conductor. Press Y. Sorry, press S. Select the outer conductor. Go to waveguide port. -3 into the height of the substrate. Click OK. In the simulation, just choose setup solver, apply, and then start the simulation. Okay. So it will take some time to simulate. Meanwhile, let's discuss the antenna parameters, and then we'll analyze the parameters. Fine. Can you see my PPT? Is my PPT visible? Is my PPT visible?
Yes, ma'am.
Okay, fine. So it will take some time for simulation. Okay. So meanwhile, let's discuss about the antenna parameters. I hope you're clear how to design a microstrip patch antenna, how to construct the coaxial probe feed, how to give the waveguide, a waveguide board, and how to start the simulation process. Okay. So let's discuss about the antenna parameter. First one is the reflection coefficient. So the reflection coefficient is a measure of fraction of the incident signal is reflected back due to its impedance mismatch. So the expression for the reflection coefficient is the load impedance minus the characteristics impedance divided by load impedance plus the characteristics impedance. So the reflection coefficient, it should be minus 10 dB. So if it is minus 10 dB, then we can say 90% power gets transmitted or it is given to the microstrip patch antenna, and 10% power it gets reflected back. And coming to the return loss, it indicates how well the antenna is matched to its feed
Ma'am,
line. Yes,
ma'am, what is the value of reflection coefficient, ma'am?
it should be minus 10 dB. The acceptable value is minus 10 dB. If it is minus 10 dB, then we can say 90% power is transferred to the microstrip patch antenna, and only the 10% power gets reflected back.
Yes, ma'am.
Okay. So the acceptable range should be minus 10 dB. Okay. If it is less than minus 10 dB, then we can say the impedance is not matched. Right. So the return loss, coming to the return loss, indeed it indicates how well the antenna is matched to its feed line. So the match is nothing but the impedance match and reflects the fraction of power reflected back due to its impedance mismatch. So once you know the value of reflection coefficient, the delta, you can calculate the return loss. The expression for the return loss is minus 20 into log 10 of the reflection coefficient. Okay. And coming to the bandwidth, once it got simulated, let me tell you how to calculate the bandwidth. Okay. So that is your higher cutoff frequency minus the lower cutoff frequency divided by your center frequency into 100. So if the antenna is of narrow band, it is represented in percentage. If it is of broadband, you can go for ratio. Fine. Any doubt in reflection coefficient, return loss, and bandwidth? Okay, we'll move on to the next parameter, the radiation pattern. It's just a graphical representation of radiation properties of an antenna. Okay, so in the S parameter, in the scattering parameter, we can view the 2D representation. In the radiation pattern, we can view the 3D representation of the radiation properties. And it shows how the power is radiated in different direction that we are going to discuss now. And coming to the voltage standing wave ratio indicates how much power is reflected back. So if you know the reflection coefficient, you can calculate VSWR. Fine. So if your reflection coefficient is 0, that means all the power is transmitted to an element or an antenna and there is no reflection at all. If it is 0, what will be the value of VSWR? If your reflection coefficient is 0, VSWR value will be 1. That means it is a perfect match. There is no reflection. Your maximum power gets transferred to an antenna. And then the next parameter is directivity. It is represented in dBi in reference to the isotropic antenna. Okay, isotropic antenna, it radiates electromagnetic waves in all the direction. Okay, practically it is not possible. Now the directivity is a measure of how focused the antenna's radiation pattern is in a particular direction compared to an isotropic antenna. Okay, this is an expression for directivity. D is equal to 4 pi into maximum radiation intensity divided by total radiated power. Fine. Any doubts so far? Shall I move on to the next slide?
Yes, ma'am.
Okay, thank you. So the next parameter is the efficiency. So the ratio of the radiated power to the input power. Okay, so you can calculate the efficiency. There's a relationship between gain, directivity, and efficiency. Gain is nothing but how much power you are going to give it to an element, the radiating element, and how much power it is radiated. Okay, so gain is a measure of the actual power radiated by an antenna in a particular direction. Taking an account of both directivity and efficiency, gain is represented as the product of the efficiency and directivity. G represents the gain of an antenna, and eta represents the efficiency, and D represents the directivity. Right? So you can see the gain and directivity, it's directly proportional. I hope the simulation, okay, it's just 4%, you have to wait. Let's analyze all these parameters. Okay, the simulation process. So here you have to observe the result. So in this navigation tree, can you see 1D result here? Can you see the 1D result? Just click this. Here you can see S parameters. So since we are using only one port, we have only S11. S11 is your reflection coefficient. Can you see the curve? It is resonating at what frequency? So you can observe the x-axis is your frequency and y-axis is your S11. That is your S parameter. It's nothing but your reflection coefficient. So here you can choose a curve marker or add curve marker. You just click here. You can see the resonant frequency is 4.857 gigahertz and S11 is minus 24.944 dB. Fine. Is it fine? In the navigation tree, here you have 1D result. In 1D result, you can see S parameter. You can click S11. You can see the reflection coefficient of this particular rectangular microstrip patch antenna. Any doubt so far?
No, ma'am.
Yes. Fine. So let's calculate the bandwidth from this. Okay. So as I have mentioned, your S11 should be less than minus 10 dB, right? So impedance bandwidth we can calculate by at 10 dB. I'm just marking my curve marker. Okay. Similarly, it's not exactly at 10, right? Fine. What is your upper cutoff frequency? It is 4.9889 gigahertz, and your lower cutoff frequency is 4.7327. You know the center frequency, it is 4.8. Can you calculate the bandwidth and tell me what is the bandwidth of this particular rectangular microstrip patch antenna? Can anyone calculate and tell me? Your FH is 4.9889 gigahertz, and your FL is 4.7327 gigahertz, and your FC is 4.857 gigahertz. Can you calculate and tell me what is the bandwidth of this particular microstrip patch antenna? Can anyone calculate and tell me the value? What is the value of the bandwidth? You know FH, you know FL, you know FC. Bandwidth is equal to FH minus FL divided by FC into 100. Tell me the value of the bandwidth.
Ma'am,
Yes,
5.274%.
5 point
274.
274%. Okay, good. Good, Ritanya. So this is how you have to calculate the bandwidth. Fine. So you know the resonant frequency of 4.8 gigahertz. So from this minus 10 dB, you can calculate the FH as well as FL. From this, you can calculate the bandwidth. Right. Now, S parameter. Now we have to go for radiation pattern. Okay. So in order to view this in 3 dimension, just go to simulation, just note down the steps. Okay, note down the procedure. Go to simulation, click field monitor. Okay, go to simulation, click field monitor, press or click far field RCS. Okay, click far field RCS. Here we are going to design for, actually our aim is to design for 5 gigahertz, but it is not exactly resonating at 5 gigahertz. So obviously we have to go for the optimization. Just apply it and then click OK. Go to setup solver. So as I have mentioned earlier, for the optimization process, it will be very easy for you if you assign the parameter for designing a rectangular microstrip. Not only a rectangular microstrip patch antenna, whatever the design you want, you can design. Okay. So you can go for parametric to analyze.
Ma'am, your voice is breaking, ma'am.
Is it clear now?
Yes, ma'am.
So it will take some time to simulate. You have designed. Can you share your screen? Show me what you have designed. Ritanya, can you share your screen? Shall I stop sharing my screen?
Ma'am, sorry, ma'am, I have not designed, ma'am. I am in halfway. I
Okay,
have
fine,
taken the
fine.
notes and I'll continue
Uh,
later, ma'am.
okay, fine, fine. Is there anyone who have CST and anyone have done the design part? Fine. But any doubts so far?
Ma'am, could you please repeat the optimization once again, ma'am?
Optimization. Yeah, I have not. Actually, I'm waiting for this fast feed result. Once I have done this, we'll go for the optimization process. Okay. So for the optimization, we don't know at what, but like we have designed an antenna, but we have to that our antenna should radiate at 5 gigahertz. That is your objective, right? You have to design an antenna which should radiate at 5 gigahertz, but it is not radiating at 5 gigahertz. It is just radiating at 4.8 gigahertz, but I want my antenna to radiate at 5 gigahertz. Right? So what you can do is you can optimize like the parameters. You can increase the length of an microstrip patch antenna or is the width of a microstrip patch antenna. So every time, whenever you are designing it, you want to, whenever you are analyzing it, whenever you are optimizing a microstrip patch antenna, every time you have to change it manually. But we have an option called parametric sweep here. In home, you can see parametric sweep here. So using this parametric sweep, we can assign the step width and we can observe the result in the same window. Okay. So once it got simulated, I'll show you how to go for the optimization process. Fine.
Yes, ma'am.
And then when I say the impedance match, so your antenna will radiate in electromagnetic waves once the impedance gets matched. Okay. But the antenna should be purely resistive. Right? What is impedance? We will be representing impedance as R plus JX, right? We have the real term as well as the imaginary term. Right? So in the real term is nothing but your resistance, imaginary term is your reactance. Our reactance should be 0 and our resistance should be high. Right? So here you have the impedance matrix. If you just click this S11, you can see. Wait, I'll let you know this. Okay, fine. In this 1D plot, so here this is your linear curve. You can choose real and imaginary. So this dotted curve is your reactance curve, fine. And this curve is your resistance curve, fine. So what is the operating frequency? 4.8 gigahertz. At 4.8 gigahertz, you can see the resistance is high. And at this particular frequency, the resonant frequency, your reactance is 0. Can you see?
Yes, ma'am.
Okay, fine. So, um, so once the impedance gets matched, when your antenna is radiating in electromagnetic waves, your antenna should be purely resistive and the reactance should be 0. That means it should be very less. Fine. This is how you have to check the resistance as well as the reactance. sometimes we can't get, okay, sometimes we'll be struggling with the impedance matching. That time you have to go for the various designs. You have to make a slot, you have to go for additional steps to increase inductive reactance as well as the capacitive reactance to match the impedance and to resonate this particular patch antenna in particular frequency. Fine. Fine. Now I think the simulation gets over. Now in this far field, in the same navigation tree, can you see far field here? In the far field, we have given step width for 4.6 and then 4.8 as well as 5, right? So just choose absolute. So this is your polar plot. Okay. So in this far field plot, you can see the polar plot. So for the 4.6 gigahertz, your main lobe magnitude is 6.7 dBi. And then you can see the side lobe level as minus 10.7 dB. So this is your main beam. This is your side lobes. Okay, this is your main lobes and this is your side lobe. Fine. Similarly, you can view in 3D. Let me rotate and show. Can you see? The portion what you have seen in the red color is nothing but the gain. In that particular portion, your gain is maximum. So the achieved gain is 6.7. Okay, so here you can see the directivity, what is the efficiency and what is the frequency. Since our operating frequency is not 4.6 gigahertz, the gain is less. Fine. We'll see what is the gain for 4.8 gigahertz. So it is around 6.85 dBi. Okay. So the unit of gain is dBi. So can you see for 4.6 gigahertz it is around 6.7. For 4.8 it is 6.85. Similarly, we'll check for 5 gigahertz. Okay, it is around 6.95. Okay. So this is how you have to see the far field result. Now we'll move on to the optimization process. Any doubt in this? You can to view the radiation pattern, choose simulation, go to field monitor, and then you can start the simulation. You can view the result in this far field. Okay, so at the operating frequency, what is the maximum gain we have achieved? Okay. Shall we proceed? Any doubt up to this?
No, ma'am.
Yes, yes. Yes, you can ask your doubt. Am I audible?
Yes, ma'am.
Yes. Okay, let's move on to the optimization process. As I have mentioned, you can go for the parametric sweep in home. In home VBS, you can go for this parametric sweep. So let's vary the length of the patch now. Okay. Go to new sequence, just click new sequence, click new parameter. So what is the parameter I have given for the length of the patch? I think L, right? L. Okay, let it be linear sweep. So the length of the patch is 13.5 mm. I'm going to increase the length of the patch. Okay, or else let's take it from 13 to 14. Fine. 13 to 14. Step width as 0. Let's take it as 0.5 because it will take a lot of time for the simulation. So if it is only 3 simulation, it will take only few lesser time. Okay. Or else let it be 0.2. Click OK. Give start. Right. So it will ask whether you want to keep the result or whether you want to delete it. You can also store the result, or else you can delete the result. So I'm going to store the result, store current result to the new file. Click OK. So you can save whatever the name you want. For example, number 5. Okay, I'll save this result because whenever I want, I can refer this result, right? So always, whenever I'm going for the optimization process, I'll be saving this results, right? I have start the simulation. So I want everyone, I hope you have noted down the questions, right? So I want you to practice it. I want you to solve. You all have the equation. Kindly solve and then kindly practice it. So if you have any doubt, you can come and ask me. Anything you want to ask because it will take some time to simulate. If you want to interact, if you want to ask any doubt, you can ask me.
Ma'am,
Yes, yes, yes,
in
sir.
the calculation of W, we have a V naught by 2FR, right, ma'am? What is the V naught there?
It's velocity of light, 3
Okay,
into
ma'am.
10 power 8.
Okay.
You can represent using V naught or else C.
Okay, ma'am.
So in this 2D result, you can see E plane, H plane, you can see the field lines. You click it. Since it is simulating, I can't able to view now. So later, once you have done with the simulation process, you can see the E field and H plane. And also what is the surface current in that particular rectangular patch antenna. Have you all installed CST Microwave Studio in your PC? So if you want any help in the installation process, you can come and meet us. We'll help you for the installation process. Yes. So that you can start designing your own antenna. It will take some time. I'll remove this curve marker. So if you want to remove the curve marker, you can go to this curve marker, choose remove all curve marker. Similarly, you can also design a circle patch. You can choose a cylinder, you can design a circle patch. So while, or else if you want to design a ring structure, you can give your outer radius and inner radius. Okay. And you have an extrude option here. So whatever the shape you want, you can choose this extrude option and you can just click. If you double click it, it will just point a particular dimension. Whatever the shape you want, you can design using this extrude option. So try to explore the CST Microwave Studio. We have a lot more options. So if you want to, if for example, if you want to design a microsтрip patch antenna, but you're not able to design one by one, right? So we have an option called mirror transform. Okay, in this transform, you can rotate your patch. You can transform. That means you can create the same mirror image, and then you can just I'll show you once it got simulated. Now I'll show you this options. Okay, and you can also bend. If you are going for the conformal antennas, if you want to bend it, you can. Here you have an option called bend. You can bend it. Since it is simulating, all these options are disabled. So once it completed, I'll show you all these things. So once this optimization process got over, we'll go for gain versus frequency plot. So for any doubt, anything you want to ask? Have you all noted down the question? Have you all noted down this problem? Your resonant frequency is 5.6 gigahertz. So kindly work out and find out the parameter values. Once you find the parameter values, start your own antenna. Start to design your own antenna. Okay. Parallelly, you can also design. If I get another curve, I'll show you how it is varying. Once you vary any dimension, and also you can also vary the dimension of or the position of the feed. So here we have given the x center as minus 3.5 mm and y center as 3.5 mm. You can also vary the position of the feed. If you vary the position of the feed also, your operating frequency varies. Fine.
Yes.
Okay. Any doubt from your side? Anything you want to ask?
Could you say how to find the those two radiuses, ma'am, like 4.7 and 1.4? How to find it?
You want me to repeat it? Fine. Now,
Like we have to put the like it's a trial and error method, or is there any standard method to do it?
no. Have you seen it? Have you seen the characteristics impedance Z Z naught?
No, ma'am.
I'll show you again. Actually, it is simulating. You have to go to home. Just note down the procedure. Go to home. Click
Okay, ma'am.
macros. Here you have macros. Click macros. In macros, you will be having an option called calculate. Click calculate. I'm
Okay,
sorry.
ma'am.
Then click calculate analytical impedance.
Yes, ma'am. And then?
Once you choose calculate analytical impedance, you will be getting an impedance calculation window. Here, what you have to do
Okay,
is
ma'am.
at the bottom, can you see the impedance static here, Z0 value as 50.11 ohm? Can you see?
Yes, ma'am.
So, like we have to choose radius of the inner conductor and outer conductor. We should. It's not like a trial and error method. We have to choose a proper dimension at your characteristics impedance as 50 ohm. For example, if I give 2.3, my characteristics impedance will be around 28 something. Okay. Then I have just increased the diameter of the outer conductor. Then I have observed it should be closely equal to 50 ohm. Right. So once I
Okay.
get 50 ohm, I'll be coming to know what is the diameter of your inner conductor and what is the diameter of your outer conductor. So while designing it, it will ask for the radius. So you have to give, for example, for this is not for the design what we have done. This is for the 5.6 gigahertz. For the 5.6 gigahertz, your inner conductor diameter is 0.7. So we have to give 0.7 divided by 2 as the radius of the inner conductor. And the outer conductor diameter is 2.35 mm. So the radius of the outer conductor should be 2.35 mm divided by 2. That's how we have to calculate the uh, dimensions. Right? I hope I have cleared your doubt.
Yes, ma'am. Thank you, ma'am.
Thank you. It's taking time. I hope just 20% more. So if it gets completed, I'll show you, at least if I get 2 response, I'll show you how to analyze it. Okay. Fine. Can you see when the length of the patch is 13 mm? What is the operating frequency here? It is around 5 point something, right? Around 5.05 gigahertz. Around like I can't choose a curve marker. I think. So it is simulating. I couldn't able to. Few options are disabled here. So at 13.2 mm, what is the operating frequency? It is not above 5 gigahertz, right? It is below 5 gigahertz. So we can choose 13.1 mm as our length of the patch so that exactly we may get 5 gigahertz as your resonant frequency. Can you understand? Can you understand how to do the optimization process? So
Yes, ma'am.
I just varied every time. I didn't go back and I didn't vary the dimension of the length or else the width of the patch. I just went to the parametric sweep. I have given the step size from 13 mm to 14 mm. I just varied the varied the dimension of the patch. For 13 L is equal to 13 mm. My operating frequency is more than 5 gigahertz. But for 13.2 mm, my operating frequency is less than 5 gigahertz. So if you want to get exactly 5 gigahertz, you can choose the dimension in between these two. Fine. So from this, I'll conclude it because it will take time for 13.4 giga for the length of the patch is 13.4, 13.6, 13.8 till 14 mm. It will take time to simulate. Okay. So I'll just can you see my slide? I'll summarize what we have seen today. Can you see my slide?
Yes, ma'am.
Is my slide visible? Yes. Okay. Let me quickly summarize what we have seen today. So we have seen the introduction about the microstrip patch antenna. It is a printed antenna. So we'll be using PCB technology to fabricate microstrip patch antenna. And then we have discussed about various shapes of microstrip patch antenna. Then we have discussed about different feeding techniques, that is your microstrip line feed, your coaxial probe feed, proximity coupling feed, as well as the aperture coupling feed. And then we have considered a problem. And then for the dielectric constant is 4.3, and then the resonant frequency has 5.6 gigahertz, and the height of the substrate as 1.6 gigahertz. So we have how to calculate the dimension of the patch. We have seen first you have to calculate the width of the patch, and then you have to calculate the effective dielectric constant. Then you have to calculate del L, and then you have to calculate the effective length. After calculating the effective length, you can calculate the actual length. Okay, so we are just calculating the effective length because of the fringing effect, as I have explained earlier. So once you have calculated the actual length, you have to calculate the ground plane dimension. Right. So once you have done that, you have to go for the coaxial probe design. You have to construct the outer conductor and then the inner conductor, and then you have to apply the waveguide port. So don't forget to add the patch as well as your inner conductor and ground as well as your outer conductor. Okay, before applying the waveguide port, I want you to add these two. You can go to Boolean and you can add it. Then after that, you can apply the waveguide port. Then go to the setup solver and then start your simulation. Observe your S parameter result. What is your S11 and what is the operating frequency? What is the resonant frequency? Okay. So we have designed a rectangular microstrip patch antenna using a coaxial probe feed, and we have analyzed the results. So with this, I'll conclude. I took some images from C.A. Balanis' book. Thank you.
Thank you so much, ma'am, for today's session. So today's session truly enriched our understanding of antenna simulation, analysis, and evaluation, ma'am. So despite the network issue, thank you for being patient, and I also thank the participants for their enthusiasm in today's session. Ma'am, I'll get in touch with you so that you can share the presentation as well as the CST file. I've also shared
Yes,
your
sir.
email in this chat so that the participants can ask doubts if they want.
Yes, yes, sure.
Thank you so much, ma'am.
Thank you so much. And sorry, I apologize for this technical glitch. And I hope we'll meet again our colleagues are very productive to come and ask me. So thank you for your patience and thank you for the opportunity.
Yes, ma'am. Thank you so much, ma'am.
Thank you. Thank you so much.
Participants do fill the attendance form shared in the chat.
I'll share this PPT to Umesh or Deepika. Like you can share your email ID. Like I'll share this PPT.
Sorry, ma'am, your voice is breaking.
If you want, like I'll share this PPT to you. Like if you share your email ID, I'll share this
Yes,
PPT
ma'am.
for your
Yes, ma'am.
reference.
Yes, ma'am.